Okay, so I'm very happy to be here. So the purpose of today's lecture, so there I listed some references which I will follow, and then also it's a rough plan for what I'm going to do in these lectures. So that plan is only tentative because I haven't finished the later part of the lectures yet, so that might change. So the goal of this lecture, the goal of my lectures is to use ADS-FT to understand low energy behavior of an interacting fermionic system. Okay. So the keywords here is low energy and fermions. And of course, interacting is also keywords, but this is some sense in trivial keywords. So our goal is to try to use the gravity approach, try to shed some light on the physics of interacting fermionic system. So I will start by give you some motivations and why actually such kind of questions are interesting, and why they're not only interesting but also important. So I will start with our current formulation. So I will start with a very quick review of our current understanding of the low energy behavior of an interacting system. So that's so-called the Landau's Fermi liquid theory. So of course I don't have time really to give a thorough review of this theory, and so what I will do is just to highlight certain conceptual aspects of the Fermi liquid theory to set the stage for what I'm going to discuss from the gravity approach. So the Fermi liquid theory is really one of the cornerstones of our understanding of many body systems. And essentially, this is our only formulation, our only general framework to understand an interacting fermionic system. And it's also tremendously successful, and it underlies our understanding for metals, semiconductors, for example, magnets, superfluids, and superconductors, etc. So this is really remarkable and fundamental framework. So talk about the Fermi liquid theory. Let me start with undergraduate quantum mechanics. So let's consider a long-interacting fermionic gas. Say for example, consider for example electron gas, a free electron gas. Say in the box. So let's consider I have a box. So this is and you put some free fermions there. Put some free fermions there. So the ground state of a system, is described, as we are familiar with, is that if you go to momentum space, and then the ground state is described by so-called the Fermi surface, is that you feel all the states, all the states in momentum space, up to some radius kf. So throughout my lectures, I will always consider spherically symmetric system. So kf will always be just will always be as rotational is symmetric. So the ground state of the system is that the all states inside Kf are filled, and everything outside are empty. And so the energy at the Fermi surface, which is normally called the Fermi energy, where to m, say for example, m is the electron mass or the fermionic mass you are interested in. So this is also the chemical potential of the system. It's because by definition the chemical potential is the amount of energy you need to put in by adding one more particle. So if you want to add one more particle, you can only add outside the Fermi surface, and so that also gives you the chemical potential. And also the nature of this ground state also determines what is your low energy excitations. Also determines what your low energy excitations. So the low energy excitations are essentially just you can say add some. The only way you can add the particle to this system is to add outside the Fermi surface, because everything inside is filled, and to the Pauli principle you can only add to outside. And so this is called the particle. This is a particle. In the free theory, this is a real stable particle. And we are interested in, say, we are often interested in the free energy of this particle. Say I will define since respect to the chemical potential, so it would be the energy of this particle minus the chemical potential. Minus the chemical potential. So that just gives you Kf divided by m. K minus Kf, etc. So this is also called Fermi velocity, and yeah. So for particle outside, for the ground state, the particle, the state for the particle outside is empty, and the particle outside have a positive energy, a positive free energy, and of course the state inside then have a negative energy, and the vacuum is to fill all your negative energy states. But of course you can also remove a particle, remove such a negative energy particle. Then you get a hole. Then you get a hole, and the hole have a positive energy corresponding to removing a negative energy particle. So hole will have momentum k smaller than kf. Yeah. Of course, you can also have the excitation like a particle and hole excitations, and more than one pair of particle and holes, etc. So this is the story. If you have a free electron gas, and so this behavior determines all the properties of the system, say all the physical properties of the system. So now let's consider interactions. Now let us consider interactions. So this interaction in principle can be strong, does not have to be weak. So now let's turn on the interaction between the fermions. The detailed form of the interaction will not be very important. So the Fermi liquid theory is based on two postulates. So Fermi liquid series, I will shorthand the Fermi liquid theory just by FL. So Fermi liquid theory based on two postulates. So the first is again that the ground state is characterized by a Fermi surface, in momentum space, and with all states inside the inside field. Okay. So this is the first hypothesis. In the podium. Oh, okay. Okay, so the second aspect of the lambda Fermi liquid theory. Okay, good. There's a board behind it. So the second aspect is that the low energy excitations so this first aspect is very similar to the free theory. And the second aspect is also very similar. So Landau postulated that the low energy excitations for even if you make the system interacting, and could even be strongly interacting, are described by so-called quasiparticles and quasi-holes. Okay. And the quasiparticle and quasi-holes, again, similar to the free theory. Oh, this board cannot move. Okay. So the quasiparticle, quasi-hole, similar to the free theory, is labeled, say, by the momentum either outside the Fermi surface or the inside the Fermi surface. Okay. So again, so you have you can excite particles outside the Fermi surface, and that's quasiparticles and quasi-holes. And so those quasiparticle, quasi-holes, they carry, say, if the original fermions carry some charge, then they carry exactly the same charge as the original particles, and also they obey Fermi statistics. So, but there's also some difference between these so-called quasiparticles and quasi-holes with the free story. So the first aspect is that the so again, the energy of a quasiparticle. So now I will use QP just to as a shorthand for the quasiparticle. And also I will just use the language of quasiparticle, but whatever I say will also apply to quasi-holes. And so just for simplicity, I will always use say quasiparticle. For quasi-holes, you just go to the negative energy. You just go to the negative energy and small k smaller than kf. So the energy of a quasiparticle again can be specified by its energy. Again we are interested in the free energy, which is by difference with the chemical potential. And again, the chemical potential is specified by the Fermi energy at the Fermi surface. And now we don't know the precise form. Now we don't know the precise form of the, say, we don't necessarily know the precise form of the energy. But as far as the dispersion relation is non-singular, you always have a linear piece, and then we'll have a higher order piece. And then this is again defines your Fermi velocity. Again defines your Fermi velocity. And so we can also write. So we will write. We can introduce a quantity called effective mass. Is we can write Vf as Kf, which is your Fermi momentum. Then define a quantity m star. So I will define a quantity m star, which is essentially the ratio between these two. The ratio between these two. And so this m star is called effective mass. And this effective mass typically is different from the original non-interacting particle mass. Say, for example, in the case of the electron, it will be generally different from the original electron mass. Say in the absence of the or the single particle. So this is the first aspect, is that this quasiparticle actually have a different effective mass. So the second is that now, of course, we are considering interacting system, and then the quasiparticles, they actually interact with each other. So quasiparticle, quasi-holes, they interact with each other. So they interact with each other. So the simplest way to think about it, say let's consider, so the ground state distribution so let me use nk to denote the distribution of the quasiparticles. And then the ground state distribution is just given by, you fill all the states, say, you fill all the states, say, with selective energy, but the state with positive energy are all empty. Okay, so now if we consider generic excited states, so if we excite some quasiparticles or quasi-holes, and then we introduce then you will have a different distribution nk, and so we can define delta nk of this nk divided by nk0. Which is the now should be vector. So nk0, and then so for such a distribution, then another postulate that you can just expand, say, your total free energy around the free theory in terms of this delta nk. And then the first order, of course, just given by sigma k, delta nk. So that's just energy of each quasiparticle, the difference from the vacuum. And then they're also intact. So in my notation, I will always ignore the spin here. Okay, and etc. So they do intact, and so this f is normally, it's some phonological parameter, which is normally called Landau parameter. Logical parameters. And the third aspect is that the quasiparticles or quasipoles can decay, because this is also reasonable from if you're in the interacting system. So a quasiparticle like this, so if you have a quasiparticle corresponding to excitation of a particle outside the Fermi surface, can in principle, say, decay through interactions, decay into one particle and one particle whole pair, or say one particle and with additional pair, say, of the particle and the holes, etc. Okay, so in the interaction theory principle, they can decay. Of course, the precise decay rate depends on the specific interactions of the system. But one remarkable thing is that a particle, due to the energy conservation, if you have a particle, say of energy epsilon, when you decay into such as 3 particles, and the total final energy of the 3 particles or holes should add up to your original, so the energy should be conserved. Yeah, for example, the energy should be conserved. And if this epsilon, the energy of the quasiparticle, is sufficiently small, then from very simple phase space estimate, if this energy is, say, epsilon, then both the final decay product of all 3 particles, their sum should be equal to epsilon. And since all of them should have positive energy, so each of them can only have energy from 0 to epsilon, etc. So if you have so for excitation very close to the Fermi surface, then you have very small limited phase space. And you can easily estimate yourself, and it's just one line, that the first space suppression is proportional to epsilon square, the energy of this original particle. And this is much, much smaller than the energy of the particle itself. And so we say this quasiparticle is actually almost stable, close to the Fermi surface. So this is a very important. This is a very important self-consistency check for this self-consistent requirement for this formulation. Because otherwise, if the particle decays very quickly, and then you cannot really call it a particle.
Can you explain the units in that equation?
You mean the? Yeah. So everything else will be normalized by the chemical potential, the Fermi energy. Yeah.
Okay, so you put in mu at any time there.
Yeah. For example, you divide by mu. Yeah. Okay. Yeah. So this is a very so this is a self-consistent requirement. So this is based on the. So of course, for this to be valid, it's important that you assume the interaction become non-singular approach to the Fermi surface. Otherwise, this argument does not apply. And also this argument does not apply when you go to one dimension, say 1 plus 1 dimension. And the kinematics in the 1 plus 1 dimension is different, and that will also changes your story. Okay, so. Sorry?
I mean, the gamma scales as epsilon squared. Does that depend on space-time dimensions?
No, that does not depend on space-time dimension. Yeah. But does not apply for 1 plus 1 dimension.
Sorry. So this seems to be actually rather extreme in the sense that you said this applies when the electrons are strongly interacting.
Yeah. Yeah.
Are still like electrons.
Yeah.
Some principle.
Yes, that's a good point. I will go back to this point a little bit later. Yeah, so that's a very good point. I will go back to this point a bit later. And so wait a couple of minutes. So so this is the Fermi liquid. So that's essentially all. So this concept of Quasiparticle is extremely powerful, because now with this ABC, with this postulate of the Quasiparticles as low energy excitations, and based on this ABC, a part of ABC I mentioned earlier, I think I have a specified ABC of specified the property of the Quasiparticles. So the concept of Quasiparticle is very powerful. Without knowing independent details of the microscopic interactions, independent of the details of the microscopic interactions, just from this ABC I was written down before, you can deduce all the thermodynamic just essentially anything. All the low energy properties of the system. Thermodynamic, transport, collective behavior, etc. Okay. Yes? Oh, you can also do finite temperature. Temperature not too high. So we are interested in the low energy property of the system.
How do you turn on the temperature? How do you do that?
Oh.
What do you have to change?
Yeah. So all the concept will apply. So the only thing finite temperature give you is give you an equilibrium distribution of the Quasiparticles. Yeah. So the ground state distribution. So at the zero temperature, the ground state distribution is for everything to be filled inside the Fermi surface. So if you turn on a little bit temperature, so So this only works for the very low temperature, say temperature small compared to the Fermi energy. And if you're turning on the small temperature, then essentially you will have a equilibrium distribution of the quasiparticles and the quasi-holes, and that's it. Yeah, and then essentially the same story apply. Yeah, I will not. Unfortunately, I will not have time to go into the details of the finite temperature, but the general principle will apply. Just you replace your equilibrium. You replace your ground state distribution with the quasiparticles by that of the finite temperature one. Yeah, here I'm just trying to emphasize a conceptual aspect of the story, and I'll try to give you a complete overview. So essentially, you can work out everything you want to know regarding the system without knowing any detailed microscopic of the theory. And of course, the theory is determined by a few the so-called Landau phenomenological parameters. But still, it's powerful enough. You can make many predictions, etc. And this is a tremendous, as I mentioned, this is tremendously successful and very powerful. And up to 1980s, essentially explains everything we know about the interacting fermionic system. And for example, let me just mention some specific predictions of this theory. Is that you can calculate the specific heat of the system. The specific heat you find is proportional to the temperature, and the low temperature is proportional to the temperature, and this gamma is proportional to this effective mass, m star. And also the low temperature resistivity, you can also calculate the charge transport. Low temperature resistivity, and this is proportional. So this is given by rho 0. Some residual resistivity depends on the system, and then a quadratic piece proportional to T squared. So this is an electronic contribution. In principle, in the solid, there could be other contributions. For example, if you can see the electron system, so this is an electron contribution. And you can also, through a more detailed study, you can show that this T square is, this square in the T square is actually correlated with this epsilon square I was mentioning earlier, just relate to the decay of the quasiparticle itself. So this is very intuitive, is that the resistivity or conductivity essentially is related to the decay of a current, and that's also related to the decay of the particle itself. Okay.
Does the relation C has temperature dependence?
Sorry?
Does the relation C has the temperature dependence?
Which C?
The gamma scale.
Gamma is a constant. You mean this gamma? Sorry? Decay rate. Yeah, decay rate have temperature dependence. The decay rate certainly the prefactor will have temperature dependence.
The prefactor?
Yeah, certainly. Yeah. Okay. Yeah. So decay rate will be. Sorry, I should say this following. The decay rate is proportional to at the finite temperature is to the max. Is roughly proportional to epsilon and T squared. Which one is bigger? Yeah, just controlled by these two. Exactly the same argument. Just at the finite temperature, if temperature is higher than epsilon, and then essentially your excitation is controlled by temperature. Exactly the same phase space argument. Any other questions? Okay. So now let me make some comments. Now let me make some remarks. Now let me make some remarks. So the first remark is, say, if we for weakly interacting, say if we have a weakly, so this is the question which I think Daniel, yeah. So this is the question which Daniel mentioned earlier, asked earlier. Say if we consider a weakly interacting fermionic gas, then the Fermi liquid theory actually from the say as the maybe some kind of small perturbation of the free fermionic gas, then the Fermi liquid theory sounds very reasonable. So you still have a Fermi surface, and then the particle still behaves similar to original particles, etc. And except they can decay, etc., with a very small decay rate, etc. But the remarkable thing is that the Fermi liquid theory actually can in principle apply to strongly interacting systems. So the interaction between these many particles don't have to be small. Okay. So can principle. Apply to interactions. Strong. Okay. So then in this aspect, so first just to show you that actually in the typical, first just to give you an example that in real life examples, indeed the example, the interaction can in principle be strong. You can see from the way that M star, so M star with the effective mass can be considered as some kind of effectively many body physics renormalized mass compared to your, say, single particle mass. So from just from comparing the M star, the magnitude of M star to the original single particle mass, you can get a feeling how strong the interaction is. Okay. So in the helium-3, so helium-3 is a Fermi liquid. Helium-3 is a Fermi liquid. So this is so neutral helium atoms. It's a fermionic particle, and it's a fermion. It's a Fermi liquid. It can be described by Fermi liquid. For the helium-3, the M star is 2.8, the helium particle itself. So 2.8 is not a very small renormalization. So it's not a small renormalization. So this indicates that for the helium-3, actually the interaction is not very weak. And also more interestingly, they're called, there's a family called the heavy fermion metals. The heavy fermion metals. The heavy fermion metals. And for those heavy fermion metals, so there's a huge number of them, hundreds of materials, etc. And M star, so inside there is an electron gas. So M star can be 10 to the 2 to 10 to the 3 times of the original electron mass. So you have a huge renormalization of the electron mass. Okay. So that indicates this many body interaction, in fact, is really strong, cannot be considered as, certainly cannot be considered as a small perturbation, but remarkably, and the Fermi liquid series still works very well. And the quasiparticles, in some sense, still resemble the original electrons, even though their mass becomes so different. Yes.
Some kind of unitarity value that says M star is always bigger than M. If I think about a free theory plus interaction.
Yeah, there is some kind of argument like this. I don't know whether there is a precise argument like that. And so there is this kind of so-called Landau backflow argument. And say if you have electron moving in the Fermi liquid, and then because it's polarized surrounding medium, then there will be backflow of the particle around it. And then when you add together, then effective velocity becomes smaller, and then it seems like you have effective bigger mass. But other than that, actually, I don't know whether there's any rigorous arguments. Yeah, but maybe other people are more expert than this can have a better answer than that. So Sansik, Subir, Joe.
Galileo varying system M star or whatever is related to a Landau parameter.
Yeah, it's a random parameter.
F1s over 3.
Yeah, but that one can in principle be lacteal, right?
Can be negative.
Yeah, in principle be lacteal. Yeah, so the only heuristic argument I know is this kind of backflow argument, which seems to say it's, yeah.
The M star, there is a limit M star bigger than 0.
Yeah. Okay, good. So are there examples which M star actually becomes smaller than M? Are there long such examples? Okay. Yes?
Can you comment on this FKK prime in this, for example, for helium-3, what it is, how we can think about it?
Sorry?
Can you comment about FKK, these Landau parameters?
Yeah.
In terms of, for example, helium, what
Yeah.
are they?
This is just depend on what you precisely asking. So this is just some kind of physiological parameter you can determine from the say what you do is that starting with this formula you calculate your observables, say spin susceptibility or charge susceptibility, and then those quantities will depend on this Landau parameter. And then you try to compare experiment, then you can determine those physiological parameters. And the important thing is that the same parameter can appear in different observables, so there are consistency checks between them.
First of all, do they depend on M star?
Yeah, it's related to M star. So as to be commented, M star can be expressed. So normally what you do is you expand this thing in terms of spherical harmonics, and then just become a discrete set of parameters. And so the M star will depend on one of those parameters. Can be related to one of those parameters.
Can I ask a question?
Yeah.
Does this also apply in neutron stars where strong interactions, as well as QED, become important?
Yeah, I would think so. Yeah. But for neutron star, how well it applies, I don't know. In principle, you can. Yeah. You have something to say?
Yeah, neutron stars, yes, it will, but for QED, there's a long-range gate interaction, and as you're going, it does break down.
Yeah.
If finite density of relativistic electrons interacting with a photon, then it doesn't work.
Yeah, right. Okay, so so it's remarkable. So from this perspective, it's rather remarkable that actually this Landau Fermi liquid theory actually works so well, because because in the strongly interacting system, there's no reason. First, there's no reason why the low energy excitations should behave like particles, and it's even more surprising why such particles actually resemble the original particles. Okay, so explanation. So explanation of this remarkable robustness of Fermi liquid theory it's a post-dictionary explanation. So a post-dictionary explanation explanation of, since we already know the answer, so now we can give explanation. So explanation why actually Fermi liquid works so well has been given from an effective field theory point of view. Field theory and RG point of view. by Polchinski and Shankar. So the idea is the following, is that at least from the experiment we know that the even that this Fermi liquid, say the low energy, we know there's a Fermi surface, and we know there are particles which resemble say original electrons, etc. And then based on this, say, experimental fact, one can try to write down the low energy effective action, the energy effective theory. So this means low energy effective theory for such fermionic excitations around the Fermi surface. Okay. So the key point is that let's assume there are some kind of fermionic particle-like excitations around the Fermi surface. There are some Fermi. First let's assume there's some Fermi surface, and then assume that there are some fermionic excitations, say particle-like excitation around the Fermi surface. And then from effective field theory point of view, you can just write down the most general action, say of this. Say imagine this psi creates such a particle. Then you can just write down the most general action you can write down, say non-singular action. Say you can imagine to describe the low energy theory, say consistent with the symmetry and the kinematics of the Fermi surface, etc. And then one can show due to the kinematics, so I will again not do it here. There will be another lecture. So you can go to original papers. I can, if you want, I can give you them. Due to the kinematical constraints of a Fermi surface, with the consecutive, you can show that all interactions you can write down non-singular interactions. All interactions you can write down are irrelevant as no energies. So if you run the RG flow, then all these complicated things, they eventually go away. Then you go back to like a free fermion theory, of course with some renormalized parameters. Except, 1 second, let me just finish this sentence. Except for two cases. So first is the forward scattering. Forward scattering. So it turns out for forward scattering, the interaction remain marginal. So the reason to understand that the forward scattering is special is very easy. If you imagine you have a Fermi surface, so at the low energy, the excitations live very close to the Fermi surface. So let's imagine if you have, say, starting with initial state K1 and K2, two particles scattered from each other. Okay. Then you can easily convince yourself due to momentum conservation or due to momentum conservation or energy conservation, the only way for the final particles to again lie on the Fermi surface is that you have a forward scattering. There's no other way to do it. So this is a heuristic reason the forward scattering remains marginal at low energies. And also this is also the difference from the one-dimensional case. In the 1 + 1 dimension, there's only forward scattering. And the second is so-called the Cooper channel instability. Is that if you have some kind of attraction between the, say, Cooper pairs, say the fermions at opposite end of the Fermi surface, diagonal opposite end of the Fermi surface, and then such kind of attractive interaction is actually marginally relevant. relevant. So of course, this is what leads to the famous to the superconductivity, BCS superconductivity.
Considering why force scattering is not small.
Yeah, sorry?
Considering why force scattering is not small.
Yeah, just they say this psi force scattering is marginal. It's because the this is something kinematic you can check yourself, but the physical argument is that for the forward scattering you can guarantee kinematically the initial state and the final state are all lie on the Fermi surface. Yeah. For example, So that makes the scaling argument different from other kind of scattering which does not lie on the Fermi surface.
Maybe a remark. So
okay.
At low energies, you can think of the Fermi on the Fermi surface as 1D Fermi. Finally, all the scaling are exactly like a 1D relativistic theory. But for many scattering events, the initial and final states don't lie on the Fermi surface. Because you account for the fact that you're sitting, and only for these forward scattering events.
Yep.
There is no phase space constraint in the scaling arguments, it's just like in 1D. Only for forward scattering.
And so thanks to Subir for collaboration. And precisely those forward scattering parameters, those forward scattering couplings, they give rise to these Landau parameters. Okay. So the Landau parameters can be considered as a phenomenological, which I wrote down earlier, can be considered as a phenomenological parameterization of those forward scattering interactions. Forward scattering just you don't change your direction. So you start with k, you scatter still k. Yeah. And
So if you look at the naive dimension of that psi force term,
yeah.
it doesn't seem like it doesn't look like a marginal.
Yeah, you have to do a little bit more careful analysis incorporating the how you define the scaling, etc. You only scale along the radial direction, don't scale around the transverse direction, etc. Yeah, so there's a little bit of argument in going there. Yeah.
Where is the mass term of the action?
Oh, the mass term of the action. So the mass term of the action is encoded here. Mass is encoded here. Yeah, this is a non-relativistic particle. This is when you expand it, it's always like linear dispersion relation. The mass is encoded here, the effective mass.
Which parameter in the Fermi liquid theory takes care of the Cooper?
So it's related to the that's also related to this four Fermi, some component of this four Fermi interaction. It's also related.
It's in this F as well.
That's actually not in the F. So F only encodes the forward scattering. The F you mean the Landau parameter.
Yeah. The only thing that is in the Fermi liquid theory is the F and this M star.
Right. Yeah, but so that's before they know this. Of course, if you write down the most general full Fermi interaction, there is this Cooper channel too. You can write down something like Cooper channel. Yeah, that's not in the Landau's phenomenological original F parameter. So this RG argument is very nice. So it tells us first it tells us this Fermi liquid is a fixed point of, in principle, some complicated many-body interaction, microscopic interaction. It's a low-energy fixed point for that. Up to, say, it's almost stable fixed point up to this superconducting stability. But this does not tell us, but of course this RG argument also leaves some very interesting questions. It does not directly tell us why, actually, if we start with some kind of UV description of the system, say UV Lagrangian, whether the system will actually flow to this particular fixed point. Or whether there exists some other fixed point or not, okay? So the purpose of my lecture is actually try to explore the possible other fixed points, say of such kind of possible some other fixed point of the many-body interactions. So before I do that, so let me turn to a little bit the technical aspect of the story. So how do we describe a quasiparticle theoretically? So in the Landau theory, they just postulate it. And but if you start with, say, if you start with a macroscopic theory, you can also formulate the quasiparticle more precisely using theoretical machinery, using field theoretical machinery. So let me tend to a little bit to that, and then I will describe development which have shown the Fermi liquid does not apply in certain situations. So the last comment is how do we see quasiparticles? Okay. So theoretically, from the field theory language, the existence of a quasiparticle of a system. So if you have, suppose you have a field theory description of this many-body system, then the existence of the quasiparticle can be verified from the low energy behavior. Rise can be verified by examining the low energy behavior of the retarded Green function of the electron operator. Say if we consider the case of an electron, and then say electron operator. Okay, so let me try to outline this argument because this will play a very important role in what I'm going to do later. So again, let me start with a free Fermi gas. So start with a free Fermi gas. So for the free Fermi gas, so everything is free. So for example, we can expand. Say we can write down the full time evolution of the electron operator. So this corresponding to a part which you annihilate particles. CK. And say a part which create holes. Yeah, etc. And so you can write down the full time evolution of your, say, Heisenberg operator. And then, so C dagger and B dagger then create your single particle state. Single particle or single hole states. And those states are absolutely stable. They're stable particles because we are considering free theory. So CK. So if I denote the omega to be the ground state, and the CK acting on the omega, then we'll create the single particle states. Okay, for K greater than Kf will be the single particle states. Okay. So the propagating of this particle will just like an ordinary scene, propagate like exponential epsilon t. So say the wave function of this particle will have a part proportional to exponential minus epsilon kt. Okay. So now let's consider the retarded Green function, say, of this electron operator. So evaluating these finite density states, say the vacuum expectation value. You can also do it finite temperature. You can then go to Fourier space. free space. So this is a free theory. So I'm sure all of you know this in your heart. Is that this will be just given by epsilon k plus I eta. So I eta is the epsilon prescription. So I use eta so that you distinguish from this epsilon. So this is the so let's give you this retarded Green function. And the fact that this Fick dagger create a single particle, propagating single particle, is reflected that, for example, when you Fourier transform this, say, you can see the TK. So suppose you Fourier transform only along the omega direction and keep the momentum direction. So because there's a pole, so there's a pole in the complex frequency plane. Compact frequency plane sitting very close to the real axis, just differed by this eta, which is just epsilon prescription. And then you find that this particle does not propagate. So this Green function is 0 for t smaller than 0. But for t greater than 0, just like a propagating particle. Okay, just like a propagating particle. So this is just like a propagating particle of this. Yeah, just describe the propagate. So this retarded Green function essentially describes the propagation of this single particle forward in time. Okay. So now let's look at the Fermi liquid case. So now let's consider what's happening in the Fermi liquid case. Talking about the particle, not the whole. We can do both, right? We can do both. So for the whole, the epsilon k will be smaller than 0. For the whole, the epsilon k will be smaller than 0. So Spear mentions an important point. So when pole, so the omega, so when the pole appears on the positive omega side, positive real part then corresponding to a particle, and if the pole appears on negative omega side then corresponding to a hole, and corresponding to a hole. So now we can go to the interacting case. Now we can go to interacting case. So now let's go to the Fermi liquid case. So here I will not try to derive the precise retarded Green function, but I will give you a heuristic argument to derive the. I will not give a rigorous argument, only a heuristic argument to derive the form of the retarded Green function for the Fermi liquid case. So in the Fermi liquid case, now again we can consider such a creation operator acting on the vacuum. Okay. So in this theory, we have single quasiparticle state. Okay, single quasiparticle state. So now use this K, the single quasiparticle state. And a single quasiparticle state. So this is not exact state because the quasiparticle decay. But if the decay rate is small, then at least at the approximate level, we can write down a state in your Hilbert space corresponding to such a single quasiparticle state. And of course, in general, in the interacting case, just as familiar in the field theory, and generically, you can also now in such a creation operator, you can also create a multi-particle state. Multiple, say, quasi-particle or quasi-hole state. Okay. Yeah, just like ordinary in quantum field theory. And so, of course, if we normalize, say this CK dagger to be have the canonical normalization, and then normalize this state, and then that means the coefficient here, if I call z, that means that z must be smaller than 1, because because this will be canonical normalized, and there's other things here, so this z has to be smaller than 1. Okay, so this z tells you the overlap of your electron operator to the quasiparticle, single quasiparticle state. Yes?
The states on the right-hand side are free series?
No, they're not free series states. They are what I postulated earlier, this quasiparticle state. Okay.
You're somehow assuming that these states are orthogonal to a high approximation?
I'm saying that this is a approximate way to write this state is because there's a very a small decay rate. The single particle can decay into multiple particle states. But if that rate is small, then I can write them approximately like this. So this is a heuristic argument. And then your electron operator acting in the vacuum then this Z will describe some kind of overlap with your single particle state, with the single quasiparticle state. Okay. Yes? Just generic is there. It's not why we did it. Just of course, in the free theory case, then this is 1, then this is the end of the story. But just from our experience of quantum field theory, generically, for the field to operate on the vacuum, generically you can create the multi-particle states. Yeah, we just write down the most general possible thing. So this is just a writing of most general possible thing, which is consistent with the symmetry. Yeah, this is not the postulate. This is just writing down the most general possibility. Yes? Sorry?
You're quantizing the theory in terms of quasiparticles.
Yeah, so
Then you should have a creation operator for the quasiparticles.
yeah, there will be you can write down approximate creation operator to create just this single particle. But that creation operator will differ very complicatedly to the original electron operator. And when we define, when we say define our retarded Green function, etc., we always started with our original field theoretical operator. Yeah.
So the quasiparticles are unstable, so those operators don't
Yeah. So you can define only them approximately. You can define them approximately. Anyway, this is just the most general way you can parameterize this state. Assuming you can write down the single quasiparticle state and the multiple quasiparticle state, this is the most general way you can write down this this electron operator acting on the vacuum.
So
Yes.
the way I've always thought about this, tell me I'm wrong,
Okay.
is that the thing on the left-hand side is like injecting a real free electron into the sample from
Yeah.
the side, and then you're expanding that in this quasiparticle test.
That's right. Yeah.
So do you mean you put the whole Hilbert space into the direct sum of one particle subspace and the two particle subspace and etc.
Yeah, exactly. Say, let me state maybe I didn't state my assumptions clear. So first, let me say, just from experiment, or suppose we want to formulate this non-Fermi liquid theory, so using this field theoretical language. So our starting assumption is that this theory possesses approximate quasiparticle states. And they can be approximated as some single particle states. And then, based on that assumption, then I can write down my Hilbert space in terms of the single quasiparticle states and the multiple particle states, etc. And now, for any state in the system, so this is corresponding to I create the electron in the vacuum, real physical electron in the vacuum, and then that can be expanded in this quasiparticle state basis.
And you never assume that the multi-particle state amplitude is less
No, I don't have to assume anything. This Z can be 0 too. I'm just parameterize the whole thing. Yeah. Sure. I'm just saying in principle can be 0, but I'm just trying to parameter. Just the way I parameterize it can be anything.
Which one can be 0? So the total momentum of the multiple state is also K, isn't it?
Yeah. Of course, momentum energy has to conserve, and charge has to conserve. Yeah, just based on all the conservations, and you can just expand whatever you want.
Which one can be 0 single?
Sorry?
Which one can be 0 single particle amplitude or multi-particle?
Sorry?
Which one can be 0 multi-particle?
In principle, we don't know anything about the system, so anything can be 0 here. We don't know. But I'm just writing down the most general parameterization. So the basic assumption of the Landau Fermi liquid theory is that Z is not 0. In order for the Fermi liquid theory to work, Z has to be non-zero. So this is assumption. When I write down this equation, I don't make any assumption other than the Quasiparticle exists. And then actually you have to make the assumption together. Yeah, anyway. So you write down this basis and you assume Z is not equal to 0. So that's the Fermi liquid statement.
So that's just like LSC. The field just needs to have some overlap.
Exactly. That's right. Exactly.
So LSC formulas is usually done for a massive field theory. So in a massive field theory, a particle of mass m, then below mass energy 3m, or if it's a bipolar field theory, there's only the quasi-particle. It's absolutely stable and the only state. But in the Fermi liquid theory, particles are massless. But the LSC formalism becomes asymptotically exact as you approach the Fermi surface, because only
right.
there is mixing between the multi-particle states.
Right. Okay, so let me start from here. And then this K will evolve with time, more or less as we expect. It will evolve with time with its own energy. But also you have a small decay rate. Okay, say compared to 0. So this will have an ordinary phase factor, but we also have a phase factor. And we all have a real part, which corresponds to the decay rate. Okay. And now, in this case, again, just based on very similar argument, the fact that the retarded Green function written in the mixed basis of T and K should describe the propagating of such a thing. It should have a component of the single particle state and plus, say, those a continuum of multi-particle states. Okay. And so assuming so again, this your retarded Green function should describe a propagation like this.
Why is square root of Z and not Z?
Sorry?
Why does it square root? Because
Sorry, say it again.
One brand keep product together, and then each has a square root of Z.
Which one? Gamma, you mean the gamma?
No.
Oh, square root. Oh, okay, sorry. That's Z. That's right. Thank you. So you would expect that the evolution of this particle will like this. So just on physical ground, then we expect the retarded Green function, say in the mixed momentum and time, will also propagate like this. So then that tells us the retarded Green function momentum space should have a pole at Z omega minus epsilon K plus I gamma over 2. Okay, and then plus other p's corresponding to the continuum contribution. So this corresponding to a pole in the complex frequency plane. Now it's finite distance from the real axis. Finite distance from the real axis, and described in such a Quasiparticle. So the important things, as I mentioned earlier, so this gamma is dependent on your kinematics, is restrained phase space, so the gamma is proportional to omega square. So depending on your frequencies, it's proportional to omega square. And this epsilon k have a linear dispersion relation. Okay. So this form. So suppose you don't know whether a theory has quasiparticle or not, but you can compute. You can compute. And now you can just calculate this retarded Green function for that, say, whatever operator you're interested in. If you find this form, and then that will tell you, say, with this behavior, linear dispersion relation, gamma proportional to omega square, then that will tell you this theory is most likely a Fermi liquid. And the Z, which normally called this quasiparticle weight, just become the residue of the pole. Become the residue of the pole. Actually, I only have 3 minutes, so let me just mention one thing. So very important part of the retarded Green function is so-called the spectral function. Of course, in principle, you don't have to use a retarded Green function to see such things. So retarded Green function is just a convenient way to see it. There's another important quantity. It's called the spectral function. Another important quantity is the spectral function. So this is the imaginary part of the retarded Green function. So spectral function is very important. It's because it's actually controls the spectral decomposition of your theory for any correlation functions. So, for example, the full retarded Green function can be written in terms of, say, the integral of this spectral function. And similarly, you can write down all other you can write down all other 2-point correlation functions, say, in terms of the spectral function. So yeah, say Feynman or anything else. So for the free gas, if you take the imaginary part of the retarded Green function we've written down before, then that just gives you a delta function for any k. It just gives you a delta function for any k. And for the Fermi liquid, if you use this form, take the imaginary part of this, now you get a spread out Lorentzian. For the Fermi liquid, you get some spread out Lorentzian. Okay. And in particular, so as I said earlier, as the gamma goes to 0, gamma divided by epsilon k goes to 0 very fast as k goes to kf, because the gamma scales as epsilon k square, as well as scales as epsilon k square, and so as k goes to kf, then the spectral function become like a delta function at the kf. So at kf, the decay rate goes to 0, so the particle become stable, become absolutely stable, and then you just get the delta function. So to draw it in picture, is that for the free case, if I consider a k omega as a function of omega for some k, say vary k, but as a function of omega, for the free gas, then everywhere I just have a sharp delta function 9 of weight 1. So you integrate this delta function, you get 1. You get 1. And so this is for k smaller than kf. And then this 9 moves as you change k, at k equal to kf moves to here. And when k greater than kf moves to somewhere there. Okay. So in the free particle, this spectral function just gives you a sharp single particle. So for the interacting case, Fermi liquid case, so for the Fermi liquid case, so you have some kind of a spread out part of the, say, a multi-particle contribution, but then there's a peak given by this Lorentzian peak, say some Lorentzian peak, etc. And so this is at epsilon k. So the width is proportional to epsilon k squared. So I have a lateral width proportional to epsilon squared. And as you change k, approach kf, then this thing becomes higher and narrower. And when you reach k equal to kf, then you reach omega equal to 0, because at k equal to kf, this becomes 0, and then become a sharp theta function, and then become again a peak on the other side, for k greater than kf. Okay, so this sharp theta function have weight z, smaller than 1, controlled by this one, controlled by that expression, z smaller than 1.
I think this is the right place to stop.
Okay. So this is the right place to stop. Let me just say one more sentence. So this spectral function is very important, also from the experimental point of view. It's because the spectral function can be directly actually measured experimentally using so-called photon emission experiment. So you shine some photon into the material and you kick out some electrons. So from the absorption, from the say absorption cross section, you can deduce this spectral function. So this spectral function is something can be directly measured from the experiment. So from the experiment, you can in principle directly map out this kind of plot, and to see to find out where is the Fermi surface. So that's where you have a sharp theta function peak, etc. And So by measuring the spectral function in the experiment, you can directly probe whether the system have a Fermi surface or not, and what's the behavior of the small excitations. So I will stop here.